last year, Google, his interests are deep learning and physics, and today he's going to be talking about adaptive quantum state tomography.
Thank you very much for the introduction, and thanks a lot for coming. Good afternoon. My name is Stanislav. I'm a PhD student here, and has been, said before, I'll just have to repeat it. I work. Thanks a lot. I work with Professor Suryak in Google in between neuroscience, physics, and computer science, kind of in between fields between these three interesting domains. And my research can be categorized into two broad directions. One of them is theories of deep learning. And there I try to understand deep learning systems, these very powerful functional approximators that we have deployed successfully in a range of interesting problems in the past. And we've been actually able to solve things that we didn't even dream of solving before 10 years ago. But the actual theoretical understanding of why these systems work so well lags behind the practice significantly. And so that's one direction in which I try to understand the science of deep learning, theories of deep learning. I actually spent last year as a full-time AI researcher in Google Research, where I started and led a few small-scale projects aimed at this direction of deep learning understanding. The second broad direction of my research is applications of deep learning and AI in physics, the intersection between physics and AI. And there I mainly focused on astrophysics and quantum. And of course, for this talk in particular, the quantum direction is way more relevant, so that's what I will stick with. And in this particular talk, I'll be discussing a particular project I did in the span of the last 2 years with my great collaborators, Igor Kwek from here. She's a PhD student here at Applied Physics working in EE on a range of quantum topics. And with Hui Kun Ang from Singapore, who was a senior member of the collaboration. And this is Igor. And the thing below that is the ideal Platonic representation of me. But so this talk will be structured roughly as follows. I will first discuss deep learning, AI, ML, and differentiable programming as concepts and why they are relevant to physics, and try to kind of narrow down conceptually where I would like to stay in the talk. In the second part, I will discuss quantum state tomography generically as a problem and why it's important and how it works, what is actually the task at hand. And the third part will be focusing specifically on our application of deep learning to quantum state tomography called neural adaptive quantum state tomography. It's an algorithm we developed. And in that part, I will describe how it works, why it works so well, why it's faster than current approaches while having similar accuracy. And I'll also discuss some experimental evidence that we were able to uncover using the algorithm, and it's due to its very easy trainability on different types of data. Okay, so let me jump straight in to the first part of the talk, where I will discuss the conceptual framework I'll be dealing with. Good. Okay, so there's a lot of terms people kind of use interchangeably, especially in physics when they apply tools from AI. So AI is the science of making machines smart. This is kind of the generic term. And AI can be the product of AI as well. The AI as a science produces AI as an object, and that object is the smart machine. So it is a very broad category, and it's interesting and extremely useful, and I deal with that more in the first part of my research. But for our purposes, these other three terms I'll discuss are more relevant. Machine learning is a part of AI that focuses on learning things from data. So it's making machines smart based on data. Artificial intelligence, on the other hand, has other components. Planning, you can put knowledge into some graph, use it graph, but machine learning in particular uses the data to learn things from them as they are. Deep learning is a branch of machine learning where you learn these things from data using a particular kind of functional approximators called deep neural networks. So those are particular kinds of functions. It's a functional family. It's a very broad family. And that family is actually suitable for learning a lot of real-world distributions we care about. And that's why people are excited about it. And then finally, differentiable programming is a term you might not be familiar with. And that term is a broader concept than either machine learning or deep learning. And it's a branch of, I would say, AI, where you differentiate through programs. So you have a program algorithm, and that thing takes inputs and spits out outputs, and you can take differential through the whole thing. And if you have some unknown parameters in it, you might be able to specify an algorithm up to certain constants. You can learn these constants through the program. So that's the concept of differential programming. It's a relatively new concept, but it fits nicely with these previously discussed branches of AI. Okay. So now more on the differential programming, because that's the conceptual framework our algorithm is most well placed in. So what you could do here, it's not quantum at all, but what I do here, I have a function in Python, and that thing calculates the nabla of some temperature field and spits out a nabla. And what I could do is I can take a derivative through the function, partial here, partial there, with respect to the temperature field. And this is now possible due to huge progress in computational mathematics, symbolic kind of differentiation, and the groundwork of that has been laid down for the many decades before now. But the thing came to fruition recently when you could actually really scale it up and use it in these school applications. So differentiable programming, you can take a differential through programming. And this is bridging conceptually machine learning and scientific computing, because you can take differentials through scientifically meaningful applications. Another example, a thing I worked on recently was learning strategies of quantum games. So there is a CHSH game. There's a kind of gamified version of Bell's inequality. And there is Alice and Bob and referee, they exchange questions and answer those questions based on what they measure on some shared qubit psi. And in this settings, you have certain behaviors that lead to good probabilities of winning, some of them do not. But I mean, you can sit down and think about it and write down the strategy that actually maximizes the probability of winning. But you can also learn it. So I wrote a program that searches through the space of strategies of these games and then learns the optimal quantum strategies leading to the maximum probability of winning for these Alice, Bob, referee kind of triplets. And this is really cool because what I did was I wrote a program and I took a differential through it and said, how should I wiggle the parameters of these strategies in a way that would maximize the probability of winning for Alice and Bob in this cooperative game. So this is just an example. This is not the topic of the talk, but it's an example of how you can use differential programming to actually get good stuff out in the physics context. Now, let's talk about why we machine learn solutions to problems. Okay, there are problems that machine learning is not suitable for. For example, sorting. So this is a Wikipedia animation of bubble sort. And that bubble sort, that algorithm, the sorting algorithm, is best written explicitly by hand, by analysis. You think about it and write it down, and then it works. It does your task at hand. So that's an example of a problem, and there's many of them. For example, matrix inversion, where machine learning would fail quite badly if you were to learn that. On the other hand, there are problems, for example, image classification, where you have a function f eating that image and spitting out a semantically meaningful label, here a nice cute tortoise leading to a label tortoise. So that thing can be done by hand, but it's brittle, doesn't work too well, it's better learned. And for more complicated versions of this, for example, tagging, if I took a photo of you and were to kind of semantically meaningfully tag all of you as individual humans, make like a nice crop around you, that would be really hard to write down as a program by hand, but it's easy to learn. It's easy now, wasn't easy 10 years ago, but now it's relatively easy. Then there are problems that are much better when learned. For example, translation. I just took a screenshot of Google Translate in the browser, and that thing is completely learned from scratch. There's no kind of linguistics insight, not much of it actually, hidden in that neural translation machine Google uses for this translation. And it learns from raw data and learns how to translate. It's like really complicated mapping. And the point here is that mapping would be really hard to specify explicitly. If you were to write it down as there's a verb and a noun, and hence, like this should be a construct in the next language, that thing would be a really huge set of laws, rules for translation, and it's much better to be learned from data. So there's a span of problems from explicitly solvable, that being the best, to completely unlearnable, and then you can fail at doing things if you don't learn it. And this goes even to things where you would not expect deep learning would make much headway. So there's a paper from, I guess, December. The field moves really quickly, so it feels it's older, but actually from December only, from Facebook AI Research, where they used the same machinery for translation, kind of natural language understanding machinery, to do symbolic integration. And that actually works beyond the scope of the training data that came from Mathematica and symbolic differentiation and integration packages. And this is a place where you would be kind of reasonably skeptical that this would actually make any difference. But you can literally learn a symbolic solution to integration as well. So even in problems that you actually have an explicit solution for, it might be a good idea to actually learn a useful and possibly even a more powerful heuristic. Okay, so let's look at an example that's very kind of prominent. It's one of the most well-known examples of the success of deep learning in the last decade, and that's AlphaGo. It was on the cover of Nature, and it was a huge success for deep learning. It's a program that plays Go. It's a game on the board of 19 times 19, black and white stones. It's a game whose kind of branching ratio after every ply is huge. So you very soon kind of reach a limit of the search algorithm you would normally deploy to solve these problems. And humans always assume you need intuition to be able to solve this, because what you actually have to do is you have to cleverly choose the right branch to probe and not exhaustively probe all the branches. And these deep learning systems, AlphaGo in particular, managed to learn these heuristics correctly. And even though we had a classical solution that actually we could write down, the heuristic solution was better and faster than what we had before. This goes further than Go. This is a paper on AlphaZero, which was a version of AlphaGo that actually played many games at once, and it was very generic. And this one is applied to chess. And there's a program called Stockfish, which is currently one of the golden standards for computerized chess. It's way better than Deep Blue that actually managed to beat Kasparov years ago. And Stockfish probes, in this particular experiment, 700,000, actually no, 70 million different positions per, I think, unit of time, I think a second, in this particular experiment. This program, AlphaZero, probes only 80,000, and yet it's way better than the Stockfish. So the brute force of the search here is surpassed by the clever choosing of where you probe, using the learned heuristics for AlphaZero. So here we have an explicit algorithm, and again, it was better to learn heuristics. So that's kind of the message I want to kind of imprint on you, because it will be relevant to this experiment, the quantum experiment I'll be talking about. Okay, so a lot of times when you hear a physicist talking about neural networks, I'm a physicist myself, so it's okay to say, they often imagine a very amorphous structure, something like this. And this is a fully connected network. It's got layer-like structure, so there is structure in it already. The most amorphous thing you can imagine would be kind of a all-to-all connected computational graph. And but this network is not actually very useful for many things. It's the most useful when you actually have no idea about your data. And my battery is running out. Sorry. Good. Okay. So it's the most useful when you actually have no idea about your data. But if you actually have some knowledge about your data, it's good to imprint the structure of your knowledge into the neural network architecture, or the graph, the computational graph, as people call it, of what you're doing. So this is an example of a network called WaveNet. It's a project from DeepMind from 3 years ago. Now successfully deployed to synthesize voices from your Google Assistant, and whenever Google speaks to you, it's a neural network generating the sound from the characters. And that network structure is much more kind of structured than this amorphous network right here. The thing right here is a computational graph, very stylized, because each of these blocks is actually pretty complicated. It's a stylized version of our ResNet architecture, one of them, this one. And that thing is good at seeing, at perception for vision. And you see there is structure in it. So the structure-less things were not as good as doing things as the things having a structure in it. And now this is a single unit from a neural network called the transformer. It's an architecture for natural language processing that actually is beating all the benchmarks these days in natural language as of this year. Extremely powerful. And that thing has a lot of structure in it. So actually there is a benefit from adding structure into your network that would actually kind of narrow down the prior over the space of functions and allow you to learn more efficiently and better. And in this talk, in the quantum state tomography part of the talk, I will show you a very structured network we developed. And the structure was needed to actually make it learn the problem well. So it's actually very important the structure was there. Okay, now let's switch gears and move to quantum state tomography as a problem. Let me just, okay, so I will look at a simplified version of quantum state tomography first to kind of explore what the problem is, and then I will go to the more detailed and more realistic version that people actually deal with in the lab, hopefully, and for which the algorithm we developed could be useful. And then I'll try to kind of build up the intuitions here on the simple case and then move it on to the more complicated case. It's more realistic. Okay, so we have a state psi. It's a vector in the Hilbert space. It's a pure state here, and its length is 1, and it is a vector of some dimensionality. The components are complex numbers. Okay, so but I perceive it as a vector. Like the details are the details of the physics, but for the actual mathematical problem, this is not crucial. Okay, so what we could do is we can take another vector, our measurement, and we can, another state, we build up a operator measuring in that direction, and we look at a projection of the original vector psi to the direction of n. And that projection, as you might know from quantum mechanics, is related to the probability of you measuring, if you actually measure in that direction, the outcome, let's say plus, rather than outcome minus in this experiment. Okay, so you have this setting, and you roll a dice, stochastic, random dice, and you roll it, and then with probability this, you get the outcome plus, and with probability 1 minus, that you get the outcome minus. So this is a very simple setting, but this shows you that you can take a vector, this psi, and make measurements on it, and those measurements are correlated with the way you align the vector m with the vector psi. If they're actually aligned, you'll have no chance of actually measuring the other outcome. If they're perpendicular, that's the other extreme. So in quantum state tomography, we have a box. It's a black box, so I actually made it black. There's a state, a vector, and I call it psi. And that state is hidden in a box. And so it's hidden in a box. It's a mystery box. You cannot really see it. You cannot read all the complex numbers specifying it. And what we do now is we don't see the box inside the box, but just for clarity, I'll show it here. We provide a measuring vector m, and that vector goes into the black box, projects itself with the psi, you get the probabilities, you roll the dice, and out of the box comes plus and minus. Okay, so stochastic outcome. So you provide a measurement, something is happening in the box, and you get an answer plus or minus, this binary answer, and you don't know what's in the box. Okay, so you know how it works. You know if the system had psi inside, those would be the probabilities. But from a single measurement, you cannot really infer that. Okay. Now, what you could do again is, given that you learn something about a system, you have plus or minus as the answer, you design a new measurement, and so you get a fresh new state. You didn't collapse it. Okay. Normally you would use it using the measurement, but you get a fresh new one exactly the same as it was before. And you make another measurement. You can repeat this every time you learn a bit more about the system, and you can design a new measurement. Every iteration of this cycle. And this ability to design a new measurement based on the previous measurements and the results of them is called adaptivity, and I'll discuss it later in the talk. But it's not a necessary component of this system, but it's sometimes there, sometimes useful. I'll discuss the usefulness as well later. Okay, but so you do this. You do it once, you do it twice, you do it 3 times, then you do it n times, and you learn more about a network, about the system than if you did it only once. And then you can create a series of guesses for what is actually hidden in the black box, given on the measurements you make. And there would be guess 1, guess 2, guess all the way to n. Okay, so this is the setting for quantum state tomography. There's a hidden system psi in a black box. You make n measurements on it, on fresh copies of it, so you can collapse it. And based on these measurements, you try to infer what's hidden in the black box. And it could be adaptive, so every step you can use the knowledge you already gained in the previous steps to design a better measurement that probes the nature of the system inside, given your now posterior from the previous step about what you believe is inside better. Or you can just choose random measurements. And in some settings, the random measurements are enough, and in some settings, adaptivity helps you. And to frame this in a deep learning way, you can imagine there's this mapping, there's a function that has this psi inside. It does some things, it makes a guess at the end, and you would like this psi to be as close to the guessed psi as possible, and you specify the unhappiness of yours using some metric on the states, and that would be a scalar called loss, or whatever, precision. So you would like to backpropagate through the whole thing. You would like to make this procedure as good as possible in generating as close as possible psi, given this initial psi, under your metric, that's the loss. That could be the Burgers distance, or it could be whatever, it could be L2 distance, Ln distance on the actual vectors. The details actually don't matter all too much. You would choose your physically relevant distance. And now, what is the problem, right? Like, this seems like relatively simple. But I skipped over a lot of things. So, how do you choose the next measurement? That's like one question. How do you use the previous knowledge of the stochastic outcomes and the measurements you made before to actually design the next ideal measurement? And but if you don't use adaptivity, this is not even an issue. But this other purple box is the actual problem. So how do you map these stochastic plus or minus outcomes, or more detailed outcomes, and your previous measurements into guesses that are as close as possible to the actual hidden state? Okay. So in this framework, I look at the vector psi, which is a pure state. It's just a matrix of 2 to the n complex numbers. Sorry, vector, not a matrix. But in reality, what people deal with are density matrices. And we can map the situation we have right here like so. On the pure state size, this is what we did right now. You have states that are precise, and then you would map them to rows that are matrices of that dimension times that dimension of complex numbers. And the measurements would be from the pure states and the associated operators, they would be POVMs. Positive operator values measurements. So I struggle with this acronym, I have to look it up because I call them POVMs without actually referring to the actual content. So there's this mapping, but conceptually this doesn't really change the details of the box we saw right here. It'll change the actual implementation, the way you map the state to the outcomes, but it'll actually not change the high-level structure of the problem. So what do we care about in this problem? We care about, given n measurements, how precisely we can reconstruct the state under a metric of precision of reconstruction. So let's say you want the L2 norm of the distance between the two, of the difference between the two matrices, your guess and the actual thing, to be as low as possible. So you want to minimize that given the n measurements you have. And the other question you can ask is, how much compute does it take to actually make this inference? Because you can make a very clever algorithm that could be optimal in some sense, but it would be really hard to run. Actually, you would have to wait a year or whatever. I'm making these numbers up, but you would have to wait a long time for the thing to design your next measurement is optimal in that sense. So there's these two metrics of what you care about. Now, let me go through classical versions of quantum state tomography, non-deep learning based things, and say how they work. And this is just it's not an exhaustive exposition of that, but it's just to give you an idea how these things typically work. So there is a regular quantum state tomography where you have a bunch of copies of the same density matrix, and you apply POVMs on them, get outcomes, and then there's some processing algorithm giving you the guess for what the correct state you are measuring would be. And so it's the two stages: make n measurements and get outcomes, and then process. And that processing could be done by a variety of methods. The processing could be done with papers, to be linear inversion, maximum likelihood stuff, or it could be compressed sensing. You can use different things to actually do this processing step. And for example, in the compressed sensing version, you are using a particular prior over the functions you can, the states you can learn, to actually narrow down what the thing could be and make it more efficient. So this is the classical thing. What you can note is that it's this two-stage structure, okay? Measure and then infer. The problem is measurements are expensive, so you would like to have on-the-fly kind of rolling estimates as you go. There's a cool paper called Adaptive Quantum State Tomography by Hussar and Holsby from 2011. It's a good paper, and in that paper they propose a method that uses kind of staged approach. So they make n measurements here, and based on the measurements they design the next measurement in the n+1 step. And they on a rolling out basis, they can process the data so far, and so they measure, determine the POVM, and then they produce the best guess so far in the thing. But it's kind of a rolling basis algorithm. And that algorithm creates it's trying to estimate the density, the probability density over all possible density matrices that could be kind of the answers to what you measured so far. And as you add new measurements, it's kind of making the density, the probability density distribution more spiky until it narrows down on the actual solution. That's the algorithm. The way it actually works in that algorithm, and this will be a feature we will reuse in our deep learning algorithm, so I'll actually go in depth with this step, is that they maintain a thing called a particle bank. A particle is not used here in the sense of particle physics particle. Particle is just like a guess for your solution. It's a particle in the sense of particle filter in EE, for example. And so they have a guess, they have a band of particles, particle 1, 2, and 3, different weights associated with the particles, and then they combine the weights using weighted average or some more clever technique to get a guess for what the true solution is. And they every time they get a new update, they kind of update these W's. And using a Bayesian rule, and then so they kind of gradually they gradually sample the distribution over the density matrices better and better as you add in measurements. Sometimes the distribution actually peaks too much, and then you have to resample the elements of the particle bank, and they do that. So that's another really important feature that we will actually reuse in our algorithm. So, but the general idea is that you maintain a bunch of states and in your memory, and those states have a probability associated with them, and you update these probabilities based on new information you get in, using Bayesian rule, using the maximum likelihood rule, and then you try to make the best estimate you can of this integral, which is just the given data d, and all the possible density matrices rho. You try to do this integral and get the actual estimate. But what they actually do and what we will be doing is a discrete version of this where you sum over the weights and the density matrices. Like so, yes?
Do you update the states, like the particles?
Yeah, the particles get updated as well. So not only the weights, but also the particles. Yeah. Both, yeah. Actually, that's a really good question. I'll detail it more in the last section with our algorithm. It's a crucial part of why it works. Cool. But the problem here is that this is computationally expensive. These Bayesian optimal updates are really hard to do computationally. So actual like physical classical computers analyzing the measurements and designing the next measurement and estimating the best current guess, those are just slow to run. And we actually have numbers on this. On my laptop, to some accuracies you care about, it could take weeks. I never ran it for a week, I ran it for a few days to get some estimates and we project it out. And it'll turn out eventually that a big advantage of our approach is that what we can do in seconds as a reconstruction, these algorithms would take weeks or months to process. So it's way faster. Okay, so let me start with the third section, which is actually the content of our algorithm. All right, so we call it neural adaptive quantum state tomography, not very imaginative, but it's neural because it's based on neural networks. It's adaptive because it's using adaptivity, and quantum state tomography because it's a task. And you can see the details of it in this arXiv paper right here. And it's a joint equal contributions with EWA. You see it right there. And the advantages of our approach are that we don't need to have a parameterized state ansatz, as many methods in kind of deep learning for quantum solid state stuff typically have. So we don't have to have that. It's very limiting typically. We have an exponential computational speedup, and so that's pretty cool asymptotically. But we even have kind of very small constants, so we actually get much faster processing times than what you would normally get. We learn all these things directly from the simulated data, and we can simulate density matrices and noise and all these things really nicely on a computer, so that's not a problem. It can be learned within hours on a laptop, so it's very efficient in training as well. And it works with any type of POVMs. So POVMs are of different types, these measurements, and I'll discuss what types they are and how they work. But if you have a new one and your lab is using a specific version of a subset of POVMs, you can tell us and we can retrain within 2 hours, and then we can deliver the algorithm for your particular kind of priors over what you care about. But we can model the noise as well, insert it in, see what it does. It just gives us a lot of possibilities to actually play with it a lot, because we can train fast, and we don't need to like sit down and rethink everything every time we have a new specification for the problem. And the cool thing about this is that the distance metric, the update rules, all these things are learned on the fly. So we don't have to kind of insert the prior all too strongly into the system. And that gives us a big edge over the classical algorithms. Let me go into it. So what we have is a recurrent neural network. So a recurrent neural network is a network that eats inputs and then recurses some kind of unit of computation on the fly, and then spits out some answer. And what I will draw here is the single recurrent neural network cell. The cell is the individual unit of computation. And what I'll be showing here is the graph of the computation. The graph is the kind of the nodes and the connections between the nodes of the algorithm you are actually optimizing through, or you're using for inference or training. Okay, so we've got the previous input, which is the previous guess in step T, the previous guess for the density matrix we care about. We have we have the particle band, the previous particles we maintain in the previous step of the algorithm, the previous kind of set of possible states with the associated weights. Then we have the previous guess, that's the estimate in time step T. And then we have the POVM that was used, that will be used in this step, designed by the previous step of the algorithm. This is very high level, so I'll zoom into the thing in detail in a minute. And then within this RNN cell, there's either a quantum simulator, which is a backpropagatable TensorFlow implemented version of quantum mechanics that you can actually run on the fly, and then you can sort of model how different density matrices would produce different distributions of outcomes, and you can use this to guide your kind of search for the true state. Or it could be physical measurements by an experimentalist that at every step makes the measurement the system recommends, and then inserts what the answer was. And after that, it spits out a new particle bank that is refined, so you change the weights as well as the actual density states in the bank. It spits out a confidence in its estimate and the actual estimate, the new updated estimate of the actual true state. And then it updates the measurement we make in the next step as well. And this kind of goes around for a number of steps. In a training time, we do not want to wait for experimentalists to deliver actual measurements. So we actually have a simulator sitting inside. It's a quantum simulator. And so the differential quantum simulator provides the measurements for us to train on. In the test time, so that would be inference time and deployment in the lab, the experimentalists would be inserting these results. So they would be given the POVM, and they would measure their hidden black box state. They would then supply our algorithm with the current measurement results, and then we would run the same way we would run here. It's just there would be this human bottleneck step in the middle. Now, the actual magic happens within this box. Okay, so the actual box is the actual kind of active component of the algorithm. And I zoomed into the thing right here. And what I will do now is I'll go through the details of the actual inside of the RNN cell, and then discuss what each individual component does and why it's important. So again, just remember we are within this black box, and it gets inputs, which is the particle bank from the previous step, the previous estimate, and the previous measurement. And we want to see how it actually produces the next estimates of all these things as it goes. Okay, so actually this is still a simplified version of the actual thing. I find that describing kind of code in pictures or words is like kind of words and actually looking at a code. So if you're interested in the actual details, this might not capture everything, but it captures the main essence of the thing. Okay, so we start with a bank of particles that came from the previous steps. So those are the density matrices that you might believe, the algorithm believes might be actually relevant to the actual solution. Okay, so those are kind of your samples in the space of all possible density matrices that you refined in the previous steps of the algorithm. Then what you get is the POVM, the measurement from the previous state. And you are also supplied in the training regime with the true state hidden in a black box. You don't have any access to that. Okay? And now, what you will do is you will look at each individual particle in the density matrix, in the particle bank, and you will make a fake measurement on that thing. You will use a quantum simulator to actually estimate if you were to measure with this POVM on this particle, this would be the histogram of answers from that measurement. And you do this for every single particle, and you do the same thing on your hidden density matrix as well. So here, this step is done on the fly in training regime. But in the real case, the experimentalist would just supply this box. It would be the actual measurement results from your experiment.
So that's a histogram, so the multiple measurements?
Oh, good point, yes. So I skipped that step at the beginning. There I showed it's either plus or minus. what we actually discovered is, I mean, it's kind of obvious in retrospect that actually is not that great. You should do kind of n measurements at once and then aggregate them instead of having like discrete 1 or 0 in each bin. So we do a number of measurements at once. So between each, let me just go back this. So yeah, so here the answer wouldn't be minus or plus. It would be like 20 times minus and 25 times plus instead for some discrete number of measurements, but bigger than 1. Good point. Thanks. Okay, so we make these measurements, okay, but in the training case, we do not want to have access to this true state. Like that true state should be hidden from the network. So we use a kind of veil of ignorance type of structure in the computational graph using gradient stuff. So the gradient can really flow through this true state. It should not have access to the true state, otherwise it would be cheating and just looking it up and just getting a true answer. So that's a big problem with these complicated neural architectures. You often forget that there's some access of your solution to the actual answer, and then you think miraculously works so nicely, but then you realize, oh, there was like a backdoor somewhere, and like it just like looked up the answer effectively. So you need to make really sure that this is not what's happening. Because in our prototype versions 2 years ago, this actually was happening, and I thought, oh, this is working so nicely. How is this even a big problem? And I realized it was actually effectively leaking the true information through the graph. So you need to make sure this is actually there. This block, this gradient stuff. Now, these structures here are neural networks, a symbolic representation of them. They actually don't look like this, but they're small neural networks, fully connected neural networks. And they take each of these kind of histograms of measurements and then try to estimate distances between them. So they try to estimate the distance between the true measurement and the measurements of the individual particles. And they try to measure the similarity of the particles to the actual true state based on these like noisy samples, these noisy distributions. But this is the cool part. We don't actually have to input the distance by hand. This is a learned metric, so we don't really have to say, well, if you have two distributions, this is the way you get the outcome. This is the metric based on which you should weigh these things. You learn this on the fly using these little neural networks. And now what we do is the same as before. We play with the particle bank again. So we have one particle, another particle, and there is this true state estimate of the true state, the green bar here. And then we start resampling these things and try to move them as close as possible to the actual true state. So we try to resample the bank of the particles to kind of zone onto the correct solution. But we don't actually know how to move them because we have very noisy estimates of the true thing. So this is learned as well. Kind of the way, the size of your perturbation that you would like to apply is also learned on the fly. So you don't say, well, if this is the distance between distributions, this is how much you should move in this direction. You say, well, move in random directions of this size that you guessed using neural net, and then see what happens then. Yes?
Is the number of particles like a hyperparameter?
Yeah, so number of particles is a hyperparameter, the same way it would have been for the ABQT, the Bayesian algorithm, the classical one. Yeah, correct. So the more particles we have, the better the sampling of the distribution we care about is. But the more computationally heavy the algorithm actually is. Yeah, good point. Nice. And okay, so you do this, you keep the best guesses, and you refine the bank of particles. That gives you the new better bank in the future, but also a better estimate of the actual state from the current step. And so this gives you the new bank, as I said, for the next step of the iteration, and a better estimate. But the way we do this estimate again is we don't want to bias ourselves in using these weights in this particular way. We say, well, these are the weights, do something with them using a neural net, and then combine them to the actual estimate. And this actually works better than us hand coding what should be done. So there's another neural net making a new estimate and the confidence it has in its own estimate of that state. And in case your adaptivity is on, you would design a new measurement for the next step as well. This would be this resampling theory and step right here, if you were to use that. Otherwise, it would be randomly chosen for you. And in fact, this step actually repeats itself like 3 times, and there's 18 new guesses for each particle. So those are all hyperparameters of the actual algorithm. There's a lot of engineering behind this project. So it turned out the actual idea wasn't that horrendously difficult, but the actual implementation turned out to be really difficult to nail down and make it work. So there's a lot of repetitions of this in each step of this iteration. And the actual algorithm in our paper, is very long, but even that isn't really like the full thing. There's an interesting part here I just want to bring your attention to, and that's that we use purification of states there to kind of be able to do these perturbations on density matrices in a way that would lead to a density matrix which is valid as the answer of the perturbations as well. And that step turned out to be quite computationally difficult because there is a eigenvalue decomposition going on there internally, and it turns out that operation is pretty stable in the forward pass of the network, but in the backward pass, in the derivative step in the training step of the thing, that thing has a much bigger radius of instability kind of numerically. So that turned out to be quite a problem. So how is this a different paradigm from the classical Bayesian algorithm we described before? Well, we don't have an explicit Bayesian interpretation. We have weights, particles, but we don't try to estimate any probabilities. We just let the neural networks do whatever they want with these weights. It's inspired by it, but there's no kind of direct interpretation in the Bayesian framework. We learn the similarity metric automatically using a neural network, and we also learn the update step and all these kind of parts I described before automatically on the fly. And the resampling of the bank is really fast. That is the bottleneck for the classical Bayesian algorithm. It takes a long time to optimally Bayesianly actually estimate the right thing. We do effectively the same thing typically, maybe not in all cases, but way, way faster because we learn the heuristics on the fly. We kind of didn't have to actually implement the actual detailed Bayesian computation. This is a theme I was describing at the beginning, that sometimes learning the heuristics is actually better than actually implementing the thing because typically it doesn't fail and it gives you a huge boost in performance. And the whole thing is end-to-end trained, so we can kind of retrain for whatever details of your density matrices, noise models, whatever you desire on the fly. So we don't have to kind of rethink how to do these things every time and kind of with pen and paper implement them. Okay, so how do we actually train? Well, we take a true state. This is the inference step. It makes a bunch of guesses as it goes, as the estimate, and we make a loss out of them. And that just says, well, if those are your estimates and these are that far away, well, this is how unhappy I am with your guesses. And and update yourself accordingly. And the way we update it is we take a derivative through the program, as I described before, the differentiable programming mindset. We take a derivative of that loss with respect to all the parameters and all the components I described right now. It's a huge kind of long graph you have to backpropagate through. And then these red lines are kind of the signal, the error signal passing through all the units of the network to update the little neural networks involved in the decision making inside. Let's now discuss the actual experimental evidence we have for this thing working and like what we learned physically from our experiments. The POEMs, the measurements you can make, are of different types. The way I kind of conceptualize these things is that for each qubit subspace, you have a number of legs. So there's a two-legged one, which is the basis POEM, three-legged one, which is just a triangle, four-legged one, which is the symmetric informationally complete POEM, it's a tetrahedron geometrically, and there's a six-legged one, which is the poly basis POEM. And you can go on and add legs, and as long as the members of the POEM, the matrices sum to an identity, you're good. That's a valid POEM. And we wanted to learn what actually, which of those work the best, and for which we kind of need adaptivity to boost the performance of the algorithm. Another thing you can vary here is the existence of the deployment of adaptivity, whether the adaptivity is on or off, whether you choose new random POEMs, or whether you design them by design to be as probable, as probing the actual state as possible. And the third thing, oh, there's a typo there. The third thing is how do these algorithms compare? Like the standard quantum state tomography, the Bayesian quantum state tomography, and our deep learning approach. And there's a bunch of metrics you can compare. So that makes this kind of less clear than, let's say, image classification challenge where you have accuracy as your metric. Here there's a bunch of metrics. So it's hard to say who's the winner. But you can certainly say we're competitive with all these things and all metrics and overpowered them in many others. So I'll try to go through all these kind of features or like these metrics and see how well we perform. So let me just go through this plot. On the x-axis, we have a number of copies of the state, so a number of measurements available to you in a log scale. So here is 1, so you've got 10 measurements, 200 measurements, 7, 10 million measurements available to you. Okay? And then there's reconstruction accuracy on the y-axis. It's a particular distance, it's the error of reconstruction. So And we want to see, given this number of measurements, how close can you get to the true state? So this is the distance from the true scale. So the lower the better, the closer you are to the true state. And of course, you would expect a monotonic behavior. The more measurements, the better you can reconstruct. So that's nice, it goes down. And what we're comparing here is different algorithms. And the blue line is our algorithm, and the dashed lines in different colors are the competing classical algorithms that we implemented. And you can see that within some error bounds we're certainly competitively reconstruction accuracy of the classical algorithm. So given some number of measurements, our algorithm will reconstruct the state as precisely as will the other algorithms. So that's great. So in this metric we're equal. And I have a suspicion that this kind of scaling and this kind of behavior is probably the theoretical maximum you can gain from your system, although I haven't seen a paper proving that, but it would be, yeah. So I think like given n measurements and optimal behavior, there's probably some threshold for how closely you can get to the actual state you care about. And this seems to be the line to which all the algorithms agree, so this seems to be suggestive of there being some theoretical reason for why this happens. And now, but look at these processing time numbers, okay? For this number, for 100,000 measurements, our algorithm converged to a solution in 2 seconds, while the competitor algorithm, the ABQT, converged in 7 hours on my laptop. And that's a huge difference if you're an experimentalist and want to actually estimate what next step you want to make. This would be a huge bottleneck for your research. But look at this. We didn't even run the classical algorithms that far. We just projected how long they would take. But in this regime, which is I might say not as realistic in the experimental settings with that many measurements, our algorithm takes 5 seconds while the other thing takes a week. So there's a huge difference, a huge gain in computational efficiency. And it's not only the numbers are better, they actually scale better. So asymptotically, our algorithm wins on that front as well. So this is the time complexity scaling of the algorithms. They're empirical. So if they're actually polynomial or actually logarithmic, it looks like they are, but this is not a theoretical result. It's an experimental result. So this is the number of copies on the x-axis, and on the y-axis is the processing time to converge to a good solution. The blue curve is us, and the red curve is the Bayesian optimal adaptive algorithm. Okay, so that thing, this is a log-log plot. So the straight line for the classical algorithm means it's a polynomial, it's a power law dependence. And that power law scales really badly, as all power laws do, as you increase the number. So it's a polynomial thing. On the other hand, our algorithm is logarithmic. So we actually, as you go to higher and higher numbers of measurements, our gain is better and better with respect to the other algorithm. So you see this is a 1 second line, this is a 1 minute line. Even for this large number of measurements, we are still below 1 minute, while the other algorithm already went over a week on my laptop. Those numbers depend on your hardware, of course, but the scale and the ratio will be preserved. Now, you can ask, what about these POVMs? When does the adaptivity help, and when doesn't it help? And we can answer this question because we can retrain really quickly using different types of POVMs. And we found that for basis POVMs, those are the two-legged ones, that do not actually cover the whole kind of range of potential measurements in your qubit subspaces. Adaptivity works really well. It helps you a lot with the reconstruction accuracy. This is a busy plot, but the two-legged things are the blue things. So, and the solid line is the thing without adaptivity, so there's this solid line. And then the dashed line is the thing with adaptivity, so there's the dashed line right here. And you can see this gap between them, which is caused by the adaptivity being better at exploiting and learning new things about the hidden system in a better way than measuring at random directions. For 3 legs, it helps slightly, so those would be orange curves, there's slight help, but it still doesn't do the full thing. But for 4 legs and more, and those would be the informationally complete POVMs, we see no gain at all, empirically. So if your POVMs are actually kind of covering the full space of possible results from a tetrahedron above, then there seems to be no actual practical reason to use adaptivity in your experimental setup and analysis, because there doesn't seem to be any gain you get. And we were able to do these experiments because we can retrain really efficiently on all those particular details of the experiments. Okay, well, that I think will be it. We will have some time for questions, but let me just conclude by giving an overview of what we discussed right here. So we developed a neural part, deep learning part, or at least differentiable programming part, adaptive algorithm for quantum state tomography. That algorithm works really well. It's very fast to train. It can take hours on a laptop, so very efficient. You don't need a rack of GPUs to do that. It's very fast to run. We go from polynomial scaling in the competing algorithms to logarithmic scaling in the time complexity of the actual compute used. It's very accurate in reconstruction, comparable to the Bayesian optimal algorithms people developed using theoretical insights and analysis. And it's very flexible. We can retrain for different noise models, for different POVM types, different details of the actual experiments. We can retrain relatively easily, so that gives us a lot of flexibility. A potential future action would be to look at downstream products of these density matrices. So you rarely care about the actual density matrix. You care about, let's say, the trace of it or some other kind of already processed version of the density matrix. And we could be estimating those directly rather than the actual, all the complex numbers of the density matrix. So that's a nice future direction we're looking at right now. Thank you very much.
So when you measure distance between distributions, between histograms,
Yeah.
there are many definitions existing of distance. You throw them all out, and you learn your own.
Yeah.
So the one you learn, does it resemble any of the known ones? Is it reasonable at all?
Yeah, it resembles scale divergence actually. So it's not exactly scale divergence. It seems to have other components. It's really hard to diagnose what exactly the learned distance would be. It behaves monotonic. It looks monotonic in all the other metrics we would care about, like Ln or like KL.
If it's monotonic in all the other metrics, why does it give that advantage?
That's a very good question. Yeah, so we use a combination. That's a very good question. So if we were to design just this particular component of the network at once, it might be better to kind of go for KL divergence or whatever we would kind of deem optimal, at once. But we use that number not only to kind of estimate the distances, but we also use it for other purposes within the network, within the big kind of monolith of the algorithm. And it might be the case that even though the KL divergence will be the right distance for this particular purpose, measuring distance between matrices, maybe for the update it'll be better to have a certain other metric. And since we're using it for multiple purposes, it might be that it's actually kind of optimizing jointly for many different criteria. So I agree with you that, very good question. I'm certain that if you were to design a particular task at a particular metric, it would be very easy. Maybe there would be some ideal metric you would use. But this end-to-end thing seems to have paid off in many contexts. So given that we kind of reuse that number for many kind of purposes within the network, that might be the reason why it works better. But we didn't kind of do an ablation study on this. Yes?
So you mentioned this purify step was somehow expensive. And I was wondering...
Well, it wasn't expensive, it was unstable.
Unstable.
Yeah, so we were getting... So when you kind of take a eigenvalue and eigenvector decomposition of a thing, that thing's relatively numerically stable as long as your condition number isn't like too high of the matrix you're actually doing this on. So that's take a matrix, give me eigenvalues, that's easy. But saying take a differential of the eigenvalue with respect to the initial matrix, that thing has, based on my reading around, kind of bigger radius of instability in the space of all possible parameters you might care about. So it seems to be in a regime where you were able to go in the one way, the other step, the training step, might be giving you bands or instabilities. So that was the actual technical problem.
Okay. I don't know. So the thought I had is when you're keeping track of the particles, why wouldn't you just keep track of the purifications rather than the reduced density matrices? Because then you just get the reduced ones by partial trace, and I don't know if there would be more stability that way.
Maybe, that's a good idea. We haven't tried this. Can have a look. Yeah. Thanks. I mean, we will actually need the density matrices for the measurements later. So we will actually at some point have to make the purified vector to the density matrix.
Yeah.
So
the partial trace might be more.
But this step, yeah, okay. This step might happen still somewhere because we kind of, yeah, we were to think about it a bit more. Can we use these purified vectors to get the outcomes of the measurements directly? Maybe it could be numerically more stable. Yeah, good idea, thanks. Yes?
How does your time scale with the system size?
Yeah. So, as I mentioned, there's a bunch of metrics you can kind of measure this on, and there I'm afraid like there's no such a big gain as you would hope for. So, I guess the hope would be that if you have a big Hilbert space, the actual effective part of the Hilbert space you deal with will be some small sliver of the full thing, and there you might be able to get better efficiency when you scale up the dimension. But here I don't think we get that gain. I think here the gains are mainly, I don't think in that scaling it's actually better. I think it's probably similar in that scaling. Because we still need more numbers in the density matrices. It's still like more elements of the graph. So I would try 3 qubits as well. But yeah, I don't think the scaling there is very favorable. It's not worse than other algorithms. It's probably slightly better, but it's not kind of gloriously better. Yes?
Have you tested the performance of this algorithm for states with, for example, like different forms of many-body entanglement or different log-range orders?
No, we actually were sampling the density matrices using like Haar measure. So like we try to be as kind of impartial about the prior as possible. But the big potential for this algorithm is that we can actually exploit the particular details of your states. So if there's like a huge entanglement between parts or whatever, that could be actually helping the system, and the system can learn around these details. So that's kind of the grand hope for the algorithm. Yeah. Yes?
So you mentioned noise, but what kind of noise is this talking about? Is this the noise that I have as an experimenter, where if I repeat or prepare the same state many times, I won't actually get the same state?
For example, at each step, your black box contains slightly different state. Or the POVM you prepared is slightly different. So you actually design it to be like this angle with this axis and whatever, but actually what you measure with would be like slightly different. So those are the 2 kinds of noise I can envision.
But the algorithm is robust against those types of noise, or?
The jury is still out. It's certainly robust to many noises like this, but whether it's robust to your particular noise, your particular kind of noise we would have to try. It certainly will start failing at some regime, when the noise is too big, that's for sure. And we don't really have, so far, kind of well-established boundaries between the stability and the instability. But it's certainly capable of dealing with some noise, we tried that, but we don't really know how far this goes. Good follow-up research. Yes?
So you mentioned it helps a lot when you have only 2 lags in the POVM. I wonder why is that possible, because if the POVM, your POVM, your whole scheme is fixed, right?
Oh, do what?
The POVM you are using is fixed.
Oh, no. So the POVM either is designed by the previous step of the network or is chosen at random. The POVM type is fixed. So the
POVM type is fixed, all of the scheme, right?
Yeah.
So if there's only a 2-lag POVM, it is not informationally complete.
Right. Yeah.
I mean, why is it possible to tomography such a arbitrary state with an informationally incomplete POVM? There must be some state you cannot.
Oh no, but because step to step, right? The orientation of the legs change. So in one step you measure x, in a 3D settings, if you had a classical vector, if you had a single direction, a projection along which you measure, you could measure this in one step, that in the other step, and that in the other step, and then you would have a complete picture. So it's not in the individual step you get all the knowledge, it's in between the steps in which you rotate the thing around that you can actually sample all the possible directions. So the POVM at each step doesn't give you informationally complete information, but like from step to step you can accumulate enough information. So if you choose it at random, you point it there and there and there and there, and then you kind of sample all the things. If you're clever about it, if you're using adaptivity, you can say, I measured here, let me measure perpendicular to it in the next step, and you can follow like this. You can have a more clever kind of procedure for choosing the POVM such that you extract the most information out. You might be certain along certain directions, and you don't care about those, so you measure orthogonality to those. So step by step, you can accumulate enough knowledge. That's why adaptivity seems to help for 2 lags and 3 lags, because you actually do not have complete information from individual steps. So you need to go step by step and cleverly choose how you measure.
We are talking about adaptivity helps. Are the POVM chosen adaptively or not?
Yeah.
Okay.
If they're chosen adaptively, it's a better performance than an equal performance to the informationally complete POVMs. You can get to the same level. If you are choosing them at random, they will underperform. But the four-legged POVM, the informationally complete one, the tetrahedron one, they will not underperform even if you choose them at random.
Okay, so let's thank Stanislav.